The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. Everything we know represents just 5% of the universe. What about the rest? Normal matter, protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in spacetime. This is known as 4-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified, too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical bases of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence, or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real, or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the Big Bang Theory, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past through the present and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness in a closed system, tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature, in certain situations. 2 particles can seemingly have an instant connection with each other, even if they are located at opposite ends of the universe. This phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no-communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare, or does it have a limited lifetime, destroying itself before it has the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi Paradox. There are many potential explanations for the Fermi Paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, rather, we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it is past the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us on to new heights of discovery and understanding. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, or 6,052 kilometers. It's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. Venus and Earth have a comparable structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles, or 3,200 kilometers, in diameter. Above the core lies Venus's mantle, composed of silicate rock, that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axes in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This is a phenomenon that isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. The solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters, indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles, or 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there's currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, 96.5%, with most of the remainder being nitrogen. However, there are also traces of other gases, such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers: the troposphere, extending from the surface to about 40 miles up, the mesosphere, stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers, about 12 miles, above Venus's main surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle, and arachnoids. Circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. At the outset, nothing existed. Then the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before time, is still a mystery. Yet physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the Endless Universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang is a moment in time, not a location in space, from which everything else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand that the cosmos breaks down at the Big Bang because mathematical infinities don't make sense in physics equations. During the cosmic inflation era, the universe rapidly expanded in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. During the cosmic inflation era, the universe rapidly expanded in size. The universe may have expanded exponentially after the Big Bang, tearing apart previously colliding regions of space. This period, known as inflation, is still largely theoretical but has gained favor among cosmologists as a potential explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. But further investigation revealed that the real culprit was nothing more than interplanetary dust causing interference. During the quark-gluon plasma era, the temperature of the early cosmos ranged between 7 trillion and 10 trillion degrees Fahrenheit, 4 trillion and 6 trillion degrees Celsius. Just a few milliseconds after the Big Bang, quarks, elementary particles usually confined within protons and neutrons, were free to move about at these temperatures. These quarks combined with gluons, carriers of the strong force, in a primordial state that permeated the entire universe. Scientists have replicated these conditions in particle accelerators on Earth, although the challenging to achieve state only lasted for a few fractions of a second. In the early epoch, beginning perhaps just a few thousandths of a second after the Big Bang, the universe experienced intense activity. As it expanded and cooled, it created an environment suitable for the merging of quarks into protons and neutrons. The cosmic neutrino background, which has yet to be detected, was created about 1 second after the Big Bang, when the cosmos density decreased enough for neutrinos to travel across space without interacting with anything. The first atoms formed when protons and neutrons fused together during the first 3 minutes of the universe's existence, creating the hydrogen isotope known as deuterium, along with helium and a trace amount of lithium. This process ceased as the temperature dropped, and 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this era first detected in 1965, was created when photons, which had previously collided with electrons, were able to flow without being disrupted. The Dark Ages refer to a long period when nothing in the cosmos emitted any light. This era, lasting around 100 million years, remains exceptionally challenging to study, as most of what astronomers know about the cosmos comes from studying starlight. It's difficult to piece together what happened during this time without stars to guide us. The first stars formed about 180 million years after the Big Bang when hydrogen and helium began to compress into massive spheres, creating hellish temperatures at their cores. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons produced by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's difficult to set a precise time limit on reionization since it happened so soon after the Big Bang, and its signals have been masked by subsequent gas and dust. However, scientists estimate that reionization was complete by around 500 million years after the Big Bang. Almost a billion years after the Big Bang, supermassive black holes formed at the centers of merging early galaxies, and intense quasars, visible from 12 billion light-years away, began emitting bright beams of light. During the subsequent few billion years, the universe underwent further evolution, with denser regions in the early cosmos attracting more material due to gravity. This led to the formation of a beautiful filamentary cosmic web, which slowly grew into galaxy clusters and long strands of gas and dust. Around 4.5 billion years ago, in one galaxy, a yellow star with rings of gas formed, eventually giving rise to the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. The third planet from the Sun, Earth, either retained a significant amount of water during this process or received a deluge of ice and water from comets later on. Primitive bacteria appeared on this third watery world between 3.8 and 3.5 billion years ago. These organisms eventually evolved into incredible marine creatures and massive dinosaurs that fed on vegetation. Around 200,000 years ago, upright beings capable of contemplating the vastness of space and learning about the universe's origins emerged. This isn't the final chapter, of course. The future of the cosmos remains a mystery to physicists. It depends on our ability to accurately measure the properties of dark energy, the unknown force believed to be accelerating the expansion of the universe. If the universe continues to expand forever, all the stars in all the galaxies will eventually burn out, and even black holes will evaporate, leaving behind a lifeless cosmos filled with inert energy. Alternatively, the Great Crunch, a reversal of the Big Bang where gravity overcomes dark energy's expansionary force, could occur. Another possibility is the Great Rip, where the universe tears itself apart if dark energy accelerates everything to ever greater distances. We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other materials left over after stars are born. So if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our solar system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to confirm that there are other systems of planets out there. In our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge spinning balls of gas that are 5 times as big as Jupiter. Others are massive rocky worlds many times larger than Earth. Some follow wild, erratic orbits so close to a star that they are burning up. One thing is clear, no 2 planets are the same, each one is unique. However, most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system, Mercury, Venus, Earth, and Mars, and in the outer solar system, there are 4 giant gas planets, Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the others. When our solar system was born 4.6 billion years ago, the planets started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter. And some formed far away, where it was much colder. Since the conditions were so different, the planets that emerged from them were also very different. At the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other elements. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. If you mix the ingredients just like you did with the cake, then put it in the oven and bake it, it will change. Essentially, this is what happened in the solar system. Overall, planets cook in slightly different ways depending on how close they are to the sun. Near the sun, where it is hot, gases burn off and water boils away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and no rocky planets at all. If you want planets made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the elements with high boiling point start to condense into solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and form one slightly bigger dust molecule, and they'd keep getting bigger and bigger. This process is called accretion. As these pieces got bigger, they became basically rocks. Then rocks slammed into other rocks to form boulders. Boulders smashed together to form even bigger boulders. At some point, a body becomes large enough that its gravity is strong enough to start pulling things towards it. Instead of just crashing into things and getting bigger that way, it starts actively pulling things in. At first, there were many young planets in our own solar system, maybe 100. Most of them didn't survive. If you go to the asteroid belt and look at the asteroid Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a spherical shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across, then it has enough gravity to crush itself into a sphere. Anything smaller remains an irregular shape. Every time a round baby planet crashes into something, it heats up more and more until it starts to melt. Gravity then begins to sort the heavy materials from the lighter ones. Lighter materials tend to float up and form a crusty layer, while heavier elements like most metals fall down and form a much denser core at the planet's center. Finally, the young planets begin to look like planets. But now they have to survive a period of violence and destruction, a cruel time that will determine which planets will live and which will die. After the sun was formed, all 8 of our planets came from the same cloud of dust and gas. But they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby, planet collided with planet, and most were wiped out. The early history of these planets would have been very, very violent, with many collisions happening in the final stages of each planet's growth. As these collisions occurred and objects crashed into each other, some planetesimals started to grow at the expense of others. These bodies, which would eventually become planets, grew larger and larger. As they got bigger, they absorbed all the smaller planetesimals around them, causing a lot of space debris to hit the surface of the protoplanet. After it was all over, only 4 rocky planets remained. Due to the different events that each planet experienced in the past, they are now all very different from one another. Mars is a frozen wasteland, Earth has flowing liquid water, Venus is full of volcanoes, and Mercury is small, empty, and very hot. For example, because of a massive collision, Mercury has a very thin crust and is very dense. It could have been a bigger planet in the past, but something struck it at an angle, tearing off the lighter crust and leaving only the dense core. Earth also experienced a massive impact at the end of its development. Something else struck it, tearing apart its mantle and sending the pieces into orbit around the Earth, where they came together again to form the Moon. Something similar seems to have happened to Mars. The crust of Mars is thinner in the north than in the south. One theory is that the northern hemisphere of Mars was hit by something early in its history, which blew off much of its crust, and that crust began to accumulate again in the southern hemisphere of Mars. There were two effects of all these collisions. They reduced the number of surviving baby planets, and they brought more materials to the survivors. If a collision involved something metal-rich, those chunks would tend to descend into what was becoming the core, whereas if the collision involved something light or icy, those materials would tend to float and form part of the crust instead. Near the Sun, four rocky planets were nearly complete. They were composed of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock, topped by a crust on the surface. All of these rocky planets were made the same way, from the same basic materials, but each turned out very differently, with different sizes and destinies. Space may look empty, but it's not. It's full of material blown out from the Sun. The Sun generates strong magnetic fields, which rise up in giant loops above its surface. When these fields collide, they release a storm of very hot, highly charged particles into space, known as the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash, and that flash of light is caused by an energetic particle passing through your head, interacting with the fluid in your eye. You see one of these flashes every few minutes. Solar wind could be deadly to astronauts if they were exposed to a large amount of it. During the Apollo program, there was an explosion on the Sun between two moon missions that would have killed the astronauts if they had been there. However, on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that originates from the Earth's core. Magnetic fields can be created by motion, converting the energy of motion into magnetic energy. Deep inside the Earth, a similar process occurs. As the Earth spins, the hot liquid metal flows around the solid core, converting its energy into a magnetic field that emerges from the poles. This field prevents the solar wind from entering the planet's atmosphere. If a planet has a magnetic field, it will deflect the solar wind around the planet, protecting the atmosphere and everything on the surface. When big storms of solar radiation disturb the magnetic field, spectacular light shows called auroras appear over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, much like Mars. Mars was formed the same way as Earth, but today it's cold, dry, and relatively inactive. So why have the two planets changed so much? NASA sent 2 robots to Mars in 2004 to investigate the planet. The Spirit and Opportunity rovers explored miles of Mars's surface and confirmed that it is a dry, dangerous desert with only 1% of Earth's atmosphere. However, they did find evidence that water once existed there. Mars wasn't always a dry, barren place. Strong evidence suggests that water once existed below the surface, rose to the surface, and then evaporated. In some places, we can even see ripples made by water flowing over sand, indicating that water not only existed underground but also flowed across the surface. If Mars once had water, it probably also had a substantial atmosphere. So what happened? We know that Mars had volcanoes in the past, indicating that it had a hot interior at some point. Since Mars was formed from the same materials as Earth, it likely had a hot iron core surrounded by liquid metal, which would have generated a magnetic field. The question is, where did that magnetic field go? Early in Mars history, the planet likely had a strong magnetic field, probably generated in the same way as Earth's. However, because Mars is smaller than Earth, it loses heat more quickly, which means its liquid core can solidify over time. When the core freezes completely, convection stops, the flow halts, and the magnetic field disappears. Once the magnetic shields stopped working, the solar wind blew away the atmosphere, and the water evaporated, leaving Mars a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun's heat created a very different kind of planet. These planets are massive, composed of gas, and lack solid surfaces. So far, astronomers have discovered more than 400 new planets in distant solar systems, most of which are enormous gas giants. Our solar system has 4 of these gas giants: Jupiter, Saturn, Uranus, and Neptune. Each has a thick, soupy atmosphere filled with hydrogen, helium, and methane. Why are these outer planets made of gas while the inner ones are rocky? It's very cold out here, 500 million miles from the Sun. At the beginning of the solar system, there was some dust, but mostly gas and water frozen in ice grains. It was cold enough for solid snow to form, where the large planets began to take shape. We believe that ice snowflakes stuck together to form the cores of the giant planets, which might explain why these planets grew so large. There was so much ice and gas. Their cores became about 10 times the size of Earth, generating significant gravity. This gravity was so strong that it pulled in all the surrounding gas, creating thick, soupy atmospheres that extend tens of thousands of miles. As their gravity increased, these planets grew even larger, pulling in more dust and debris, which eventually formed their moons. Jupiter and Saturn each have more than 60 moons. The gas giants also have something else unique: rings. Saturn is distinct from the other planets because of its beautiful rings, but Jupiter, Uranus, and Neptune also have rings, though they are much fainter and harder to detect. All 4 gas giants have rings, but Saturn's are the most prominent. From afar, Saturn's rings appear as a single flat disk, but in reality, they consist of thousands of small rings, each only a few miles wide. When the Cassini probe flew by, it discovered billions of pieces of ice and space debris moving within the rings at speeds of up to 50,000 miles per hour. These ice and rock fragments frequently collide, sometimes forming small moons, while others break apart, unable to grow larger because Saturn's immense gravity tears them apart. Scientists are just beginning to understand how these rings formed. One theory is that a comet collided with a moon, knocking it out of its orbit and bringing it closer to the planet. Saturn's gravity then tore the moon to pieces, and the debris became trapped in rings around the planet. However, the real mysteries of the gas giants lie deep within them, tens of thousands of miles below the clouds. This is where things become truly extreme, defying natural laws. Most of the new planets we discover orbiting distant stars are enormous gas giants. So large that Jupiter seems small by comparison. Yet, no one knows what happens inside gas giant planets, whether in our solar system or beyond. We do know that Jupiter's thick atmosphere extends 40,000 miles deep, with bands of gas moving at high speeds, creating violent storms on its surface. But what lies far below those storms remains a mystery. NASA sent the Galileo spacecraft on a 14-year mission to Jupiter to learn more. On December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, entering at a speed of 160,000 miles per hour. As it descended through the thick air, parachutes slowed its fall, revealing lightning in the clouds and winds reaching 450 miles per hour. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe after we dropped it in? It didn't hit anything. It just kept falling deeper into Jupiter's environment, with the pressure increasing as it went. It recorded pressures 23 times higher than on Earth and temperatures more than 300 degrees higher than on Earth. When you're in the environment of a gas giant and go deeper into this soup of hydrogen, which lacks a solid surface, it can still be extremely heavy. Eventually, you would be crushed by the immense weight of the material above. Although the probe only descended 124 miles before it was destroyed, it provided scientists with a glimpse of Jupiter's interior. However, the dark heart of the planet remains a mystery. Like some rocky planets, gas giants also have magnetic fields. Jupiter's magnetic field is 20,000 times stronger than Earth's, extending all the way to Saturn, over 400 million miles away. Similar to Earth, Jupiter's magnetic field shields its atmosphere from the solar wind, keeping it safe. When scientists studied Jupiter's magnetic field, they discovered that it also affects Jupiter's moons. The volcanic moon Io, which orbits only 217,000 miles from the planet, emits a ton of gas and dust into space every second. This effect is amplified by Jupiter's magnetic field, which creates powerful radiation belts, making the area around Jupiter very active. If you point a radio antenna at Jupiter, you can hear how the planet and its magnetic field interact. Jupiter and Saturn can produce auroras without the need for solar wind because they generate their own magnetic fields due to their immense size. These auroras indicate that gas planets also possess magnetic fields. But how are magnetic fields created on gas planets? On Earth, this is done by very hot liquid metal spinning around the planet's solid iron core. Gas planets likely have a similar process, but they don't have iron cores that get extremely hot. Instead, they formed around frozen cores of dust and ice. So, we don't fully understand what's happening inside gas planets. We still don't know what constitutes the deepest parts of Jupiter's interior. It's possible that Jupiter has a solid core at its center, or it could still be liquid. We might never know. No probe could ever travel the 44,000 miles to the planet's center to investigate. Galileo was destroyed before it could reach Jupiter's core. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. These are the great creative forces in planet formation, but there's one more crucial element that significantly impacts how planets develop: water. Planets may seem fixed and unchanging, but they are constantly evolving. One planet in our solar system lost its atmosphere and became a desert, another became extremely hot and transformed into a hellish environment. Earth has also undergone changes, and it was water that made all the difference. When you look at Earth from space, you see a lot of water. We are, after all, the blue planet. That would suggest Earth is very wet. Right? At first glance, our world appears to have a lot of water, with 3/4 of it covered by oceans. However, only 0.06% of Earth's mass is water. Some of this water is on the surface as oceans, and some is trapped in the planet's metal. In reality, Earth is relatively dry. The inner rocky planets, including Earth, formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away by collisions during the planet's formation. These massive collisions were so energetic that if there had been water on Earth, it would have evaporated and escaped the planet. So where did Earth's water come from? When you look at Jupiter, Saturn, Uranus, and Neptune, you see they have a lot of water locked inside them, and even more dramatically, so do their moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune is present in significant amounts. So how did some of this water end up on Earth? The answer is almost certainly that some asteroids and comets, far enough from the Sun to retain their water, brought it here. There were millions of these watery asteroids and comets that entered the inner solar system, and some of them collided with Earth. Over time, Earth accumulated the water from these asteroids, which now covers nearly the entire planet. Without surface water, life as we know it would not have existed. But what if there was too much water? The oceans would be much deeper, covering the continents and even Mount Everest. It's likely that the precise amount of water on Earth was crucial for the evolution of Homo sapiens into a technological species. About 4 billion years ago, a bombardment of comets and asteroids brought just the right amount of water to Earth, shaping the world we know today. It's possible that this same process is happening somewhere else in the universe right now. There is certainly a lot of water out there. Hydrogen is the most common atom in the universe, and oxygen is one of the next most common. H2O, water, is therefore a very common molecule, which is exactly what we see happening in our universe. So, water is abundant in the universe, and we're also finding that planets are too. However, we have yet to find another planet where water exists in liquid form. Over 400 new planets have been discovered by scientists, but none of them resemble Earth. What we haven't yet found is a planet around another star that is similar in size, mass, and chemical makeup to Earth. Finding such a planet remains an extraordinary goal for humanity as we search for other worlds that remind us of home. But we will keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what future generations will likely call the golden age of planetary exploration. For the first time, we will begin to understand just how different things are out there. This will be an exciting time, as the laws of physics and chemistry tell us how planets are formed. Many scientists believe it is only a matter of time before we find another planet like Earth, one that formed from the same materials, in the right place, with the right amount of water. One thing is certain, billions of planets are out there, waiting to be discovered. Our solar system is a harsh environment, where volcanoes are destructive forces. From the ice volcanoes of Saturn's moon Enceladus to the vast lava fields of Jupiter's moon Io, and even on our own planet Earth, it is true that we would not be here without volcanoes. Volcanoes influence and change our climate. They are both creators and destroyers of life. Today's spacecraft and observatories have revealed volcanoes on planets we once thought were dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most powerful natural forces on Earth. They create new land, destroy old land, and release gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels strange new forms of life. Volcanoes help sustain life on Earth. And now we search for signs of life on other planets. We understand that life requires water and energy, and this is where volcanoes come in, as they generate tremendous amounts of energy. If we find volcanoes on other planets, we may also discover life. The search begins with the planet closest to Earth, Venus, a planet that closely resembles our own. Venus and Earth have similar masses, and 3 billion years ago, Earth and Venus were very similar, with new land, new oceans, and an atmosphere conducive to life. However, something went wrong on Venus, causing its history to diverge drastically from Earth's. Venus took a definite turn toward the dark side a long time ago, becoming a hellish planet. Today, the surface of Venus is 900 degrees Fahrenheit, hot enough to melt some metals. In such extreme conditions, survival is impossible. Venus is a greenhouse world with an atmosphere rich in carbon dioxide, which traps solar heat like a blanket. Actual images of Venus's surface reveal a desolate, scorching landscape. The planet was devastated by its dense CO2 atmosphere, which was produced by volcanic activity. Spacecraft in orbit provided the first clues, as radar pierced through Venus's thick clouds and revealed volcanic formations spread across the planet. These formations resemble Earth's shield volcanoes, which are round and flat, named for their shape. These volcanoes ooze lava slowly, sometimes for thousands of years. When we were able to map the entire surface of Venus using cloud-penetrating radar, we began examining its landforms and discovered many familiar features. In particular, we observed enormous shield volcanoes that closely resemble those in Hawaii. The radar images of Venus were strikingly similar to those of Hawaii's shield volcanoes. In the past, Venus was home to numerous volcanoes. We were amazed when we first saw a picture of Venus and discovered a cratered volcanic surface. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of smaller ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. What could have been a home for life was instead consumed by flames. Venus's volcanoes expelled trillions of tons of carbon dioxide into the atmosphere, causing temperatures to soar and the oceans to evaporate. On Earth, carbon dioxide can be absorbed into rocks or dissolved in the ocean. But on Venus, there is no water, and the temperature is so high that carbon dioxide cannot even combine with minerals. Volcanoes released carbon dioxide into Venus's atmosphere eons ago, and as time passed, fewer and fewer processes existed to remove it. The volcanoes effectively sterilized the entire planet. If Venus ever supported life, it no longer does. Earth remains the only known planet with life, but that may change with the gas giant Jupiter and its moons, once believed to be frozen and lifeless. A mystery arises as a cloud hovers over a cold and seemingly lifeless world. On closer inspection, we see how volcanoes transformed Venus, a planet once similar to Earth, into a hyperheated inferno. The presence of volcanoes on a planet like Earth was not surprising, but the discovery of volcanoes on a moon was astonishing. In March 1979, the Voyager 1 spacecraft provided our first close-up look at Jupiter's tiny moon Io, a world once thought to be frozen and lifeless. But what they saw was extraordinary. They observed an arc next to the moon, almost as if there was a second moon behind it. We were puzzled, wondering what it could be. Everyone assumed Io was lifeless, dull, and uninteresting. Then people realized, oh my God, it's a volcanic eruption. We discovered that Io is engulfed in volcanic activity, making it geologically extremely active. There are constant volcanic eruptions, and these eruptions release a great deal of sulfur, which becomes extremely hot. Sulfur changes color with temperature, appearing red, orange, yellow, or even black. As a result, images of Io's surface look like a pizza with various types of cheese and black olive-like spots. Io is not dead, it is alive and evolving. There are more than 400 active volcanoes on Io, with the largest, Pele, erupting from a gigantic lava lake. Pele's eruptions are so massive that the lava extends approximately 400 kilometers into space. It would be an extraordinary sight to stand on the edge of that lava lake and watch the plume shoot off into the void of space. Pele's eruptions are so colossal because Io is so small. There is nothing to hold the lava back since Io has virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes look like mere fireworks in comparison. How can a moon so small be so volcanic? The answer lies with Jupiter. Just as the moon raises tides in Earth's oceans, Jupiter raises solid rock tides on Io. Io's orbit around Jupiter isn't circular. Sometimes it's closer, sometimes farther away. This varying distance allows Jupiter's gravity to exert a powerful force on Io, stretching and squeezing it every 2 days. The ground on Io rises and falls by nearly 300 feet, generating extreme heat and enormous pressure. Wherever there are weak spots in the crust, lava erupts. This means that volcanism on Io is planetary in scale, unlike Earth, where only certain areas around tectonic plates or weak regions are active. Io is an entire moon that's essentially one massive volcanic hotspot. Io is the most volcanically active body in the solar system due to the immense power of Jupiter's gravity. Volcanic activity on Io has taught us something new. It has shown that internal energy sources can drive volcanism in ways distinct from Earth. Io is a lava world, extremely hot and violent, making it hard to imagine anything surviving there. We've discovered strange volcanic eruptions on numerous planets and moons, but so far, Earth is the only place where volcanoes are linked to life, or so we thought. This is Europa, a moon that orbits Jupiter nearly 500 million miles from the Sun. Europa is a 2,000-mile-wide sphere of ice. From afar, its surface appears smooth, but up close, It's a different story. Like Io, Europa is pummeled by Jupiter's immense gravity, causing its surface to rise and bend, forming ridges and deep fissures. When we first obtained close-up images of Jupiter's moon Europa, they looked vaguely familiar. It turns out that Europa's surface resembles Arctic ice flows on Earth, and they're similar for a reason. Beneath Europa's several-mile-thick icy crust lies a global liquid ocean. Magnetic measurements indicate that this ocean is an astounding 60 miles deep. The gravitational pull from Jupiter heats Europa's rocky interior, melting the ice above. As the core is stretched and heated by tides, it's not unreasonable to believe that there could be a boundary between a hot core and a liquid water ocean. On Earth, underwater volcanic eruptions are often surrounded by life, and the same might be true on Europa. The darkness under the ice is complete, the pressure a crushing 2,000 Earth atmospheres, a harsh environment, but perhaps a cradle for life. If there's evidence of life on Earth, why not on Europa? The energy source from volcanic activity, the presence of liquid water as a universal solvent, and complex hydrocarbon chemistry all suggest that life could exist there. Life on Europa would be difficult but not impossible. On Earth, life exists in extreme conditions, searing heat, crushing pressure, and absolute darkness. Life on Europa might resemble life on Earth in unexpected ways. If life exists beneath Europa's ice, it would likely be aquatic, without eyes due to the lack of light. Organisms might feed off the energy from the volcanoes, using sonar to navigate their surroundings. Volcanoes on Europa could be the genesis of new life. It's even conceivable that Europa is typical and that this is the norm for planets with life, with Earth being the exception. Consider the possibility that Europa could serve as a model for the billions of moons in the universe with liquid oceans. Our horizon suddenly expands several billion times by looking at the moons of Jupiter. Our solar system alone is home to more than 170 moons. Multiply that by the vastness of the universe, and that's a lot of potential habitats for life. All that's required is liquid water and a source of energy, which volcanoes can provide. And volcanoes are ubiquitous. Saturn is twice as far from the Sun as Jupiter, but it also has volcanic moons. Similar to Europa, these moons could potentially support life. Saturn is one of the more unusual planets in our solar system, with a ring system 600,000 miles wide, an astounding 62 moons, and one with a secret. Enceladus is one of Saturn's lesser-known and more distant moons, and it's long been known to be covered in ice, owing to its extremely brilliant and reflective surface. However, when the Cassini spacecraft visited the planet, it made a remarkable discovery, not on the planet itself, but on Enceladus. The Cassini probe revealed a massive plume, backlit by the sun and erupting into space, providing conclusive evidence of volcanic activity. Cassini's sensors zoomed in on the south pole of the moon to capture these enormous craters scarring its surface. At the south pole of Enceladus, there are extraordinarily large fissures that open and close as Enceladus orbits Saturn due to tidal forces. These fissures are enormous, extending for hundreds of kilometers. When they begin to open, you would see a large crevasse opening at approximately 100 miles per hour along its length. It would be incredibly spectacular. Huge gravitational forces cause the surface to open and contract with incredible velocity, helping to produce the heat necessary to melt ice and form oceans beneath the surface. The conditions of the water beneath the surface of Enceladus are ideal for life. It is at the ideal temperature and would be beneficial for life. The liquid water beneath the ice would be just like seawater here on Earth, and the chemistry of the water erupting from these fissures suggests that it contains salt and organic matter. Therefore, we have identified a location in the solar system where there is a strong possibility of life existing right now. In the ice particles, Cassini has detected complex carbon molecules in conjunction with liquid water, suggesting that perhaps life could exist deep within this mysterious moon. Enceladus might not be alone. Another of Saturn's moons, Titan, might also harbor life. Titan is one of the largest moons in our solar system and the only moon with a thick atmosphere. It's a frozen world with ice as hard as rock and lakes of liquid methane. Yet, we may also discover evidence of volcanoes and the tantalizing possibility of extraterrestrial life on this planet. Volcanoes are one of the most destructive forces in the universe, as evidenced by Io's raging eruptions and Triton's ice and nitrogen explosions. Even on Saturn's enigmatic moon Titan, however, destruction can lead to the possibility of life. Titan has a diameter of 3,000 miles, making it larger than Mercury. It has the thickest atmosphere of any moon in our solar system. There is weather, including cyclones, winds, rain, and even lakes, but the temperature is so low that liquid methane replaces water. And it's loaded with essential compounds for life. Titan has proven to be one of the most fascinating locations in the solar system. It's an active world, the only moon with a dense atmosphere, an atmosphere very similar to that of Earth due to the presence of nitrogen. As it turns out, organic molecules high in Titan's atmosphere are formed when methane gas reacts with sunlight, producing compounds essential to life. But if sunlight consistently converts methane into organic compounds, why doesn't the methane run out? Methane is abundant in the atmosphere, but we know that it is quickly broken down by sunlight, so it shouldn't be there. There must be a source of methane, something on Titan that emits methane continuously. Cassini has spotted what appears to be a crater, and infrared cameras reveal that the crater is surrounded by various types of materials. Scientists believe the green areas may be volcanic, possibly plains of lava ejected from Titan's interior. On Titan, the boiling liquid emitted by volcanoes could be either ammonia or water. Methane and ethane are emitted by Titan's volcanoes, which is likely the cause of the planet's extremely dense cloud cover and orange atmosphere. This atmosphere likely originated from the outgassing of Titan's volcanoes. Even on a globe as rigid as Titan, volcanoes require heat. On Titan, there are two sources of heat. Radioactive substances heat the interior, and Saturn's enormous gravity tugs on the moon. Similar to Enceladus, these two forces produce sufficient heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan give life a chance to survive? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide everything needed for life on Titan. If life does exist on Titan, it would be truly alien. It might breathe hydrogen instead of oxygen and possibly swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane, possibly tidal pools, as well as volcanic and hydrothermal activity. Perhaps volcanic heat could produce enough energy to support life on Titan. That's speculation, but it can't be ruled out. However, we may not need to travel so far to discover signs of life. We may find it on Mars, a volcanism-rich world much closer to home. Volcanoes are ubiquitous throughout the solar system on planets such as Io, Titan, and Triton. These planets are intricate, volatile, and violent. Once, we believed that Earth was the only planet with both volcanoes and life. Now, we find volcanoes everywhere, but alien life has yet to be discovered. Volcanoes exemplify the absolute force of creation and destruction. They go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. Volcanic cauldrons are the birthplace of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, and replace the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times when the solar system was young. On a planet similar to our own. This planet is Mars. 3 billion years ago, volcanoes were active. The greatest volcano in the solar system still stands there. The cliffs leading up to it are more than 6 miles high. Even Mount Everest would be dwarfed by them. This is the formidable Olympus Mons. It covers an area the size of Arizona, with a crater 53 miles wide. A structure of this magnitude takes millions of years to form, a period of time that Earth's volcanoes never have. The Earth's crust is constantly in motion. In the depths of the Earth, a solitary hotspot forces magma to the surface, creating a new volcanic island. While the hotspot remains stationary, the surface is in motion, and the new island moves away from the hotspot, making way for another volcanic island. Mars is different. The crust is locked solid. There is simply no tectonic activity. The crust is one big, solid plate, and so if there's a hotspot, it just sits there, building and building, resulting in a larger and larger volcano. That's why Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era. Olympus, an extinct volcano on a fading planet, is now a veritable colossus due to Mars' diminished atmosphere. However, the ancient volcanic terrain of Mars could one day support life. The evidence is readily available on Earth. Volcanoes in Hawaii have formed enigmatic tunnels known as lava tubes, created when rivers of molten rock rush into the ocean. Lava tunnels are formed when there is an underground river of basaltic lava, magma, and molten rock at 2000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface, except here the crust is solid rock, and the river continues to flow beneath, creating this cave, this lava conduit. Recent images imply that Mars volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. Now, after possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This existence could be our own. Radiation will be one of the obstacles that future humans will face when attempting to live on Mars, especially during solar storms. The incoming cosmic rays could be dangerous. The tunnels and caverns of Mars' extinct volcanoes could one day serve as ideal homes, retaining air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new light. Volcanoes are capable of both destruction and creation. Aliens, are they real? Do they exist, and if so, what do they look like? Today, we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small green beings with large eyes is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So what should we do if we ever encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi Paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals, and we are too primitive to detect theirs. Regardless of the reasons, the Fermi Paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic on aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comments section below. Thanks for tuning in, and we'll see you next time. Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system, its vibrant stripes and prominent great red spot making it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant, consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 13 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones characterized by lighter-colored clouds. Conversely, its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that's been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It's thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. The exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes the frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter but also sheds light on the broader principles governing atmospheres, including our own. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is believed to have an ocean beneath its surface as well. As of my knowledge cutoff in September 2021, Jupiter was known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system. Although much fainter and smaller, Jupiter also has rings, composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnetosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system.